English. Are you recording still?
Yeah.
Okay.
I will ask in English.
Yes.
So you showed the equations of Einstein. The left-hand side was related to geometry, and the right-hand side was, as I remember, was related to mass. Or
Mass, energy, anything.
Mass, energy, anything. So is the right-hand side the part where we connect to materials?
Okay. This is quite expected. Oh, so. Okay, here's the equation, right? So what you are saying you mean is this. You explained us something today. Is what you're explaining about this? This is your question, right? Like this media part.
Yes. The right-hand side was related to media, and is that the part?
No.
Okay.
The whole work was about translating this curvature terms as if they are media parameters. So I'm telling you that I can write this metric and this R nu mu that is also written in terms of a metric is a function of that metric completely in terms of electric and magnetic permittivity transfers. This is what I'm telling you. The right hand side, what I'm doing about it is that this contains mass, right? But we don't have mass in electromagnetism. I'm telling you that that's also the slide I showed about Krypton and stuff. You can realize this decomposition that I showed you entirely electromagnetically. So I'm telling you that I could match the magnitudes of this mass density and momentum density that I talked about completely in terms of electromagnetic variables. That's what I told you. So our theory works both ways. But the problem is, we cannot reformulate our theory looking at this relationship. This is one way of looking at gravity. It is like one way of looking at quantum mechanics. I mean, you took quantum mechanics, so you know that quantum mechanics have different ways of looking at it. There's like Heisenberg picture, there's Schrödinger picture. You could formulate it in terms of wave functions, you could formulate it in terms of matrices, right? Density matrices that I talked at the start about Shannon entropy.
So this connects to the equation with the rho and small g, right?
Yeah, but again, like this formulation we didn't use. We used our mapping entirely in ADM formalism.
Okay.
This is the initial formalism. Okay. So the whole point of, that's also what I tried to explain, which I didn't probably achieve, because if you didn't understand, probably the rest didn't, because you have the most advanced knowledge in physics in the audience. So basically, the reason I explained ADM is that what I realized is that the metric in transformation optics is closely related to the metric in ADM formalism. So I thought, oh my god, if the metrics are related to each other, whether I could also transform the other equations in the ADM formalism into the media. So our work didn't happen with this formalism of general relativity. It is like trying to solve the problem in different formalism of quantum mechanics.
Thank you.
I couldn't follow the relationship of entropy to these discussions. But one thing I noticed is you mentioned rho and j at some point. I guess the unit of, I tried to calculate the units of j. It was, I guess, action, right? J joule seconds, if I'm not mistaken. So is there some significance of...
The thing is like this. There is the whole existence of these three slides is to tell you how theoretical physics and electrical engineering could interact with each other. That's the only reason I put this slide. So entropy doesn't have any importance in my discussions. So the reason I introduced entropy, telegrapher's equation, and ADS-CFT correspondence is that I realized that, not me of course, entropy, by the way, entropy and its connection to physics in communications engineering was realized by Shannon, and it was advised to Shannon by von Neumann. Von Neumann was the guy who formulated quantum mechanical entropy. So again, these things, these engineers and physicists, these interactions are going on for a long time. Probably at the heat of the moment, it was the beginning of the seminar, I didn't clearly explain, that's probably my fault. But this is the reason I explain entropy. And the reason I introduce entropy is that basically looking at these kinds of formulations, these kinds of structure, you cannot say whether the entropy needs to always increase. There's nothing in communications engineering telling you that, because the transformations need to be energy conserving. And in quantum mechanics, they need to be unitary transformations. So the only way you can say that entropy always increases is that you impose a thermodynamic variable. In quantum mechanics, this is temperature. In communication engineering, you add noise externally. And that's how you get signal-to-noise ratio. So looking at only the transformations within communication engineering, or let's say signal theory, there's no way of telling that your signal is getting distorted. So think about it. Within electrical engineering, within that theory, there's nothing by itself telling you that your signal gets noisier. That's crazy. That's crazy. Mathematically, of course. I mean, if you're an engineer, you say, I will just add it. But there's no fun in it, right? We need a formalism where it includes at the start. J is about momentum density. It is completely irrelevant. But Lagrangian, as you said, is Joule seconds, so you're right. I hope I answered your question. Yes.
I understand that this view of explaining, for example, in the mass bending to space, and I understand that in electromagnetic media, permeability and the permittivity stores the information about bending.
Exactly.
Right? This is a macroscopic view, I guess, in the electromagnetic media. But when we, for example, industry, commercially or something, we can fabricate the, for example, media. I think we should know the microscopic things. For example, what the electrons do.
Let me tell you about it. I mean, that's also one of the faults of my presentation. I should have talked about metamaterials. Again, since I'm more like a physicist, a theoretical physicist, I skipped the engineering part because I see it as boring, but I should have talked about it. Basically, metamaterials are objects where they give you the freedom to change electric and magnetic permittivity and permeability as long as you want. So these things exist in 1990s. Pendry is a great British engineer. He was in Imperial. I think that this work was actually first military. So these things were all disclosed until 2006. So yeah, these kind of transformation optics came out with the interaction with metamaterials. So the theory of storing electric and magnetic, the theory of storing geometry and permittivity and permeability actually existed in 1960s. Also Kip Thorne, that I mentioned, also had some ideas in 1980s. So the whole invisibility boom happened with the advent of advent of metamaterials. And all these initial papers by Pendry and Wolf Leonard, by Mentor, they did simultaneously. They all referenced metamaterials, so I should have mentioned that. So the whole point of invisibility is connection with the metamaterials. The physics of metamaterials and how they are connected microscopically to electrons and positrons and other stuff is the topic of many-body physics. I'm not a many-body physicist, so I can't really discuss it. Thank you. So does anyone have any questions? Oh yeah, my God.
The visibility is directional. So the material is invisible for one direction and visible for the other direction.
Well, it depends. Like, again, these are It's like asking the question: the sun or a black hole. What a black hole does? You have all seen the pictures. A black hole has a light ring around it, right? It means that it bends light so strong that light orbits the black hole. Which direction the light falls into the black hole, it orbits, right? It doesn't depend on which direction it comes. But for a metamaterial, it does actually. The angle it comes is actually an engineering problem. So you pointed out a very important problem for its engineering application. Obviously, the perfect invisibility device isn't a feasible thing, and there are a couple of reasons why, and one of the reasons is what you just asked.
And I didn't follow the place that the Laplacian equation.
Okay. I mean, it's quite natural that you didn't follow because I skipped that part. But let me tell you, I mean, are you a physicist?
No.
Okay, then I shouldn't show it because it complicates stuff. So basically what a Laplacian is basically a second order equation in space is connected to second order in time, right? And the exact solution of it is what it is? Cengiz Han?
Very
Exactly. What way?
complex expansion.
What way?
Complex expansion.
Yeah, exactly. You're the best. You see, it's a plane wave. I was expecting that answer. It's a plane wave. So again, it's like the combination of the plane waves. It's like the combination of complex exponentials. So how do I obtain that? I obtain it using something called transverse traceless gauge applied to the equations that I was discussing. So you need to know how to do calculations in GR to follow that part. So that's why I focused on the conceptual things more, because I probably didn't get that across. Yes?
I have a question, but it may be irrelevant.
It's always relevant, if you ask it.
You said that under small perturbations, the solution is in terms of plane waves. So can we say that a plane wave or a gravitational wave, there is a Huygens principle can be written?
I mean, these waves are plane waves not in the function of electric and magnetic fields. These are plane waves of electric and magnetic permeabilities. It is as if there are two different waves at the same time. One coming from the fields themselves, the plane waves that we see in our department, and the other ones coming from the material, the medium, the space-time itself. Think of it like that. And it is a linear combination of these plane waves that explain the whole system. So basically, by ignoring the rich structure of these materials, you basically obtain linearly dependent equations that we discussed in 303. That's the whole point. And using a canonical approximation, I think you can obtain a Huygens-like equation, of course. But I mean, yeah. I hope I could. Maybe I couldn't explain that part well. Maybe I didn't emphasize that they were the perturbations of permittivity and permeability. So maybe that's my mistake also. So anyone has any other questions? Okay. So thank you for coming and for your patience.